record. It's recording. Well, it's 2 p.m. guys, and we have one student. Woo! All right. So Sarah, what did it help? Moving the spot, I'm sorry. Learn. Hello. We have 2 students now. That's awesome. What's your name?
Gabe?
Gabe?
Yeah, Gabriel.
Oh, Gabriel? Gabe? Oh, got you. So, yeah, I'm here to help you. Of course. Question 3. Let's see if I can. Oh, it's inverted. Oh, I cannot do anything. Okay. Yeah. Like the right here. You see the board? I don't know how to change. That's it. There you go. Good. Good. Or business again. Okay. Yeah. Oh, for question 3. More student. Let's go. Yes. So let's see assignments. Work 1. So I can give you guys answers, but I can't explain stuff. So you're talking about 3, right? Yes. We can go over an example. So imagine this. Imagine that you have velocity time, this is distance, and then you have this, and then you have a bunch of points. That's what we call this A. C. And what I'm telling you is that this is the axis, then we have a z-axis, so we set to some value of, let's say. So what they're doing in this example is that they're describing a function velocity as some x, some y, and some z. Okay. So when you plug these points here, so we know that c is always equal to alpha. So we don't care about that. Yes.
All right, so I have a question. First of all, it's actually 3-dimensional. How do we graph that out? But can we just, okay. Third one is constant. Can we just say you can see value for all of them? But 3.
So let's see. All right. So we have all right. So what do we have there? We have, how is this thing called? I'm not looking for the word grid. No, I'm not looking for that one. but in space, something that is flat.
Right.
A plane. Okay. We have a plane, and you said that we have something constant. What is it? Yes, it's equal to alpha, right? So it's fixed. It doesn't really matter what you do with X and Y, you see, so it's always gonna be equal to alpha, right? So what you can think about that is that you have a plane,
Oh, we just move the plane up and say the plane act.
yeah, a plane that, okay, a plane that is crossing at that point alpha. And then this is your grid. It's a grid Z equals alpha. Coming to? Yeah.
Well, the,
Because all the points are gonna
Making
be
it back.
there.
you're making a vector field, right? And so the vector has
Give me back to you.
So what we're doing is, for example, let's say we have a point, x equals 5, y equals 5. So we'll do wherever that is on our graph.
So X equals 5, Y equals 5. All right, continue.
So it would have to point, can I use the equation?
Sure.
So when we get the vector of 10, comma, 5, comma, 3, and we have to point that in that direction, right?
Oh, yeah, that's right. Yeah, so you get velocity equals to, you said 10, 10, 5, 3, right? All right, okay.
So we don't have a Z coordinate to plot the origin of the vector, but we have to point it to Z equals 3.
You have a C origin. What do you mean by that?
Well,
I mean, that's the origin. Yeah,
Is that exposed or is that exposed?
that's a vector.
right, so just point.
Like, so that means, yeah, it'd be like.
Yeah, that's point.
It's slow. What do you mean by the slow?
It's everything. It's
Yeah.
It'll all be.
Okay.
What it is, and what's what is that means it's 0? Okay, right. Right, so we just put that light, that's the light. They're all pointing to through, and then just represent the vector of the. Okay.
He does my work. You do it better than I do.
I hope.
Sure. Yeah, that's what I was trying to do here.
Yeah, like.
Kind of.
On a draft.
Sure.
Well,
All right, so we're using this equation. What point do you want?
It'd be like. I guess. I don't want to choose them very, okay. I guess like, in 0.
All right, so we have X equals to 2, Y equals to 0, right?
Yeah.
All right, so we already said we're gonna be working with the grid, right? This grid sends our value in the C component constant. We can set this grid as that, right? And then this axis would either be X, Y. Right. This is one way to do it. Another way that you can do it is actually graph it in 3 dimensions and always use three. Just different way. It's not like better or worse, just a different way to look at it. That's another thing to keep in mind. Like you could definitely always do your YC and then go here to 3. The only thing in that case, you won't be able to use this grid. You won't need to use like your own and do this a bunch of times. But it's not incorrect to do it this way. Actually, Stefania, the STS, did it this way, like the answer, for the answer key. But I talked to Lewis about it because some of you guys did it this way, which is I found genius, basically because you're using the materials that you're being given, and that's also way both are correct. So we're trying to do this one because that's the one that you guys like are working.
Yeah.
So yeah, we said, well, you want to come up to a word and try to do it?
Sure.
And then I will assist you on your learning. I don't want to be just lecturing. Right, go for it.
Right, so this is the
Remember, these are points. This is velocity. And here we're plotting only vectors, not points.
Yeah.
These are points on that weird graph that I created. Not necessarily the same as it.
so then this is X squared in here.
Yeah, this is the x point, x squared. So the point squared.
And then what are the other ones?
I think this one was like y times 3.
Oh, I see, yeah. And then it's E.
C is equal to alpha. I
Oh,
put
yeah,
it
yeah.
times 3, but that defeats the point of
Okay.
I was making that C was constant.
So
Are you guys cool with what? Where I was discussing a lot with, I had a discussion with, Stefania with, I think, before.
I think it's a question for class. If you take a divergence of a gradient, does it take you back to the original function? Are they like reversible? Because one increases the number of connected.
What's the definition of a divergence? Let's start there. What's the definition of, what's that on you? What's the curl?
The gradient?
Yeah.
Um,
Wasn't that what the delta later of product?
yeah, so the gradient finds questions with respect to the independent variable. So take the scalar field vector. For the divergent, produces scalar field from a vector field. So theoretically, if you have a scalar field, you apply a gradient to your vector field. If you then apply the divergence, you get back to the same scalar field, or you get different scalar field.
If it's scalar field, for example, imagine that you have a matrix position, right? And you apply gradient, you get velocity. So the partial velocity. You can partially do this, but right, so you position at same time. But then getting back,
You get the.
I'm not sure if you get again.
Yeah.
You don't get any position.
You get the.
I think you get. Yeah,
So.
maybe 90, I'm not sure.
So the arc is very simple.
You won't be doing any of that. No, that's a good question. I'm not sure. That's what I was trying to figure out. Then you gotta do it. You're not even this zero. I'm sure. I'm sure it has an answer. Look it up. What you got? All right, so we have.
yeah, this one. Yeah, yeah, correct.
So you're saying that this start,
Well, yeah, at that point, yeah.
yeah, okay, this will be like 0, 0,
Or no, sorry, this would be origin.
first. Okay. And then this,
And it was
X4,
yeah,
right?
yeah.
Why is why you're studying?
So we're not supposed to do it at the point.
No,
So like
no,
the point,
because you're not graphing points, you're graphing the vector. You're starting from the origin.
okay,
Let's say this is like the point here. You can think it of the point of another graph or another thing, or just information that you get, and then you use it in that equation. You get a vector, and then when you're plotting in this graph are vectors. Like the points is another. If you were asked to plot the points, you would plot, but in this case, you only work with the vector.
Okay. So
You'll start the origin of that of this. Okay, so we go from 0 to 0, 4. I mean, you could also make that order.
yeah. And it would go.
Or you can also define that this was 0.
So say that was like A, and then if you're moving on to B and it was a different point.
You actually, I think you have it, right?
Yeah, different point there. So then
So you said this term,
yeah,
you put it here. X squared. How will you do that?
Oh, that would be on display.
the X direction is moving one.
Yes.
Actually, like that, you could use it like this. It'll be like over here.
So you're doing all of them from the origin?
Yeah, because that's how you define the location and direction. Based on origin.
Okay. And then
That's what makes a vector.
Wait.
yeah. And then can you clarify again why you don't do that? Like why is it not the vector
Point at
that point, I guess? Like what's the difference there?
What's the difference? Right. Imagine that you have a graph
Mhm.
like that. You have position and you have time. And then in the graph you have a lot of points, right? Like X, Y points. Well, that's data.
Yeah.
Pretty much. That's what I tried to
Yeah.
figure here. So in this data, what they're saying is that if you plot those points into an equation, so this one, then I get the velocity of the fluid, I think, in this position in this time. And then when you get it as different velocities of that liquid, let's say, over time.
Mhm.
So you get that information, you use this equation to get vectors, the stuff you can get information from, like you were saying, like about the curl or divergence.
Yeah.
And then what they are asking you to do is to use those vectors and plot. And you can plot them this way or the other way that I was talking.
Okay.
All those work fine. It's clever. You guys thought about. I didn't when I did this.
Yeah.
Is to plot it this way. I did it like 8 times this way.
Okay. Yeah. And I think the second was telling me about that way.
Yeah.
And
Either way, it's fine.
yeah, but if I don't know if I remember correctly now, but I thought she did it from like the point on that example 0, 1. So I think she went maybe 0 here, 1 here, and then she did like the vector from that origin, I guess, at that point. Rather than from the origin of the Cartesian coordinates. Does that make sense?
You look at the solution.
Okay.
Is this what, 3, right?
Yeah, 3, 3, right?
You're right.
I chose the vectors
That's
created
right.
in form,
Yeah.
or
that's
in
right.
point.
Or what? Can you describe what number 6 is? This one? That's- Yeah, basically these are equations. So you get the diffusion coefficient, which is second alpha. And then, which is with an equation, and then you'll get, I think you will find distance. But yeah, that should be given to you. You should not be able, you shouldn't like be able to solve this right now. Pretty sure that's what he meant this morning in class. The other stuff that he hasn't covered yet. In that case, you should double check. I talked to Dr. Lewis about it and I described this way. He said it was okay. And we just talked about well, I told you like different between points and vectors, and they're asking me to graph the points, the vectors, not the points. But
Yeah, from the origin.
Yeah.
In that way.
Yeah, so there are different things.
Yeah. So I guess.
Because we're talking about velocity and we're
Yeah.
talking about like time and distance in this example right here.
Yeah,
Yeah,
within the 3D system,
it will be the same. Or at least how I understand it would be like just, for example, if you got here 40 alpha, it would be 4 x 4 x y0, then alpha. So yeah, something like that. Then this
gotcha.
not necessarily from the. That's something that I can talk to Lewis and Stephanie. I think I'm right.
Okay. Is Stephanie like when you check she did it from the point?
Yeah, she did. I just checked her answer for this. Obviously, you guys don't have access right now, but
Yeah.
yeah, she does it how you described it.
Okay.
And, yeah, it's. Let me make a note of that. Oh, yeah. Please come closer. Yeah, 1.
No, I can see from here.
All right. What's oh.
And the one that he was doing. For the first thing. Starting is. Here, okay. When the first vector.
Second, sorry, don't forget that we are having a discrepancy here. Oh, here. Yeah. Sure, but so yeah, that's it.
So this like the starting.
Yeah, so this are the points that he's giving you.
Yeah.
So when, let's say this point. over.
So yeah, so point B is here, and if you run it exactly, and so the vector is these two fours here, then do you connect these to the vector? To the vector to the vector?
So what I'm saying, you gave is that each point, it's from a data you give.
Mhm.
And what you're doing then is using that data and creating a vector out of it with an equation.
Yeah.
And that equation, you get this velocity. And then what they're asking you to do with this velocity is graph.
Right.
Based on like a plane that could be in 2 dimensions, or in 2 dimensions if you are talking earlier. But what I'm saying is that the starting point is always the origin. So like, and the points are like describing that differently. They're describing, let's say, position in time, not necessarily velocity, because you need to do like an equation for the velocity.
Yeah.
So yeah, what I'm saying is like you graph them based on the origin being zeros. For example, if you're 4 alpha, this is the plan alpha, you would go 4 that way, in the x-axis, and 0 in the y-axis. Terminated there. Or you place 4 this way, alpha that way, and then in reduction. Not at the point. That's something that I need to talk to Stephanie about, because I described what describing to you here to Dr. Lewis, and he said it was correct, like using this plane as and like the homework is 3, and then we can graph the vectors, and I described that to him, and I told him it was so it was correct. And I like based on the information you get there, I don't see how you would be using those points here. It's talking about vectors. Right.
So does
And
the
stuff.
point matter in our graph?
No,
Oh, okay,
that's what I'm saying.
got it.
That's exactly what I'm saying. Thank you for asking.
Okay.
Thank you for asking. I don't know if you're understanding something.
Yeah,
so
no, that
at any
was-
time, make questions.
Yeah, I understood what you said about
Okay.
that, so the point is only defined our vector, and the point isn't used when putting a vector on the vector.
Right. Because there should be different things.
That,
Yeah, it's not super clear, but yeah. Yes. But we have to put an asterisk, because of the wrong. I'm pretty sure it should be, because I remember doing this homework. That's how I did it.
Mhm.
We have to check. So is there something about number 4 that you wanted to go over? Oh yeah, sure.
no, it's good.
You want me to erase this?
I don't know.
Let you sure was. You look like more powerful, but I don't know why. Main character earned. Oh,
Is that not just the biggest thing?
something that I have changed my life is to think that I'm the main character in my story. And I don't consider myself narcissistic, so I'm pretty sure, at least in my perspective. But people could argue. But I will say no. Yes. Yes, let's go to number 4. Ooh,
That's not, for what? That is true.
The velocity vectors channel. Next is the velocity. Yeah, what's the question?
So are you
Yes. Yeah, they're saying they're constant for sure. 5 centimeters per second for the max, and then the height of the channel is 1 centimeter. And it's saying that when the velocity of y equals to it's so basically in that case we have a channel that we have what's interesting to me is that the velocity at y equals 0, it's 0. That's strange. Because this is B max times 4y over h, right? Is that how you read this? Are you reading this? So we're thinking the velocity of the metal should be equal to V max. Correct?
This would make sense. Because there are arguments. So with reason he would have to do. But it doesn't have to.
Right. It does not. But for example, what one student did is that they added units here. So they calculated the vectors, then they added units to like meters over second. You can, I don't know, miles per year. So I don't know.
That's
Oh, it does. So I'm incorrect. So it's centimeters over second. Go ahead. They was right. Oh, yeah, it's really cool when you're from the airplanes. I normally don't. So that's the reason I would have written miles over years. We got like 5 points of that. That's okay. We live and we learn. Thankfully, we have Dave over here like guidance. So you're doing 4 right now? Will be a point. Mhm. In the vector field, yeah. That's a good question. You see what you're doing is you have this channel, and then based on this origin, your y, you're creating like different vectors. Then what you're gonna do is trying to like or see how the velocity flows through the channel, and where is the maximum velocity, where's the minimum velocity, and from there you could say like what type of liquid it is, and how it's the flow within the channel and stuff like that. It's basically what you're looking for. That's what says. You're gonna do like different y coordinates, and then like
X component here, in that time.
Yeah, that's always said. We said at the middle of the channel, y equals to 0. That's what you thought.
Well, the X doesn't matter, right? We just assuming it's X equals 0 for all of these, and just having an arrow go, so how long is, right? You can just do it. Yeah, for the point, so for.
Yeah, it says here, it says in the book.
Right. So the vector is only going to have an X component.
Yeah,
It's the Y.
Yeah.
But for the origin of the vector, we're starting it at X equals 0. right?
Yeah.
Yeah. So we're just gonna get like your graph where it's different but the arrows along the Y axis on there.
Correct.
20 hour party.
Correct. Basically, you're having a vector, and you're translating the vector into one.
Right.
And going towards possible. I think it should be possible. You could do it yourself. The other question, so it's not your goal, but you know, it's about. It was,
So for this one,
yeah, yeah,
So comparing that.
yeah.
You said that you started with them. But if you didn't. Okay.
I get what you're saying. Guess it could be like this interpretation as well, so you can understand, because here it makes sense to describe it this way because of the problem. You're in catheter, you're talking about velocity, and the velocity changes to then air base in height. And this catheter, you have to basically it tells you what to do. The other one is say, at least how I see it, not clear. You should provide one. But yeah, so we could add. I don't get back to you guys in that is to well, based on the premise that the vector, so we are asked to write a graph vector, these are points. And none of them are like we don't know if they are connected or not. I assume that the only thing that I have to basically graph a vector, and the vectors of the velocity. So every vector in my graph starts with something like that. That will be more than the nobody. So, but yeah, it's a good way to do. Especially, yeah, because here for sure. Yeah, here the actual points do matter. Yeah.
Number 5.
Number 5.
Yeah, it mentioned the length scale. And that's something that
That's basically two modes of transport.
covering one there, or
What letter?
like
Oh, yeah, he's gonna spell it for sure.
that's on one there.
Yeah.
Okay. Thank you.
Yeah. What I can the spiel, because I reviewed this from my own notes. The spiel is that. The spiel is that, let's say you have. Oh, let's see. It is time. And then you have. It's not, no, it's not. The size of the molecule stays constant. All right. And then you have here the distance. And look at it, this distance between A and B. Where A is the start, B is the finish, and B is this distance. And whatever A and B are is start and finish of the path of this molecule. That's to travel that much. So what it says is that for displacement, if you have convection is going to basically at smaller scales or smaller distances, diffusion is quicker, especially at 100 these micrometers or below. And then above that, diffusion, not convection, it's faster. I can look my notes.
That makes sense.
He's gonna talk to about this on Wednesday for sure. But
Yeah.
now that your guys are here, you ask questions, so you got to share that. Oh, okay. So it's not time. This is length. Yeah. And here you have transport time. So basically what it says is that for diffusion at really small scales, the transport time is low. So here, so this is diffusion. But for convection, so for convection along a really small scales, the transport time is high. But what happens is, and I think this 100 micrometers. Beyond this point on, convection is quicker, depending on the length scale. But below this point, diffusion is quicker. That's the reason really small scales, when you have your capillaries, oxygen is diffuses, not convexes, if that makes sense. That's the reason between any cells in your body, there is a capillary no less than 100 micrometers from it. Because the only thing that can at that level can travel is through diffusion. And since you want that oxygen in all your cells to be constant, it has to be less than 100 micrometers. So yeah, this is basically what he's going to explain on Wednesday.
The calculator looked at that.
Or
Listen to each other.
Or where you want from a cell.
Okay. What's an example of in like I guess a lot of
Let's think. What do your organs do? Where will you see what is convection for you? Oh, what do you know about convection? Okay, circulates. Convection. Circulates. What does that Like curls? Right. Right, but try to define. Or just like using the word in a sentence, but try to, what is convection? Rock, or material. Movement of materials. Beauty for, that's not necessarily true, but movement of materials. Okay, so movement. Of mass. Alright, that's the same as diffusion. You're moving mass. What's the difference? More. Also. You're moving mass, sure. That's true. The same happens. How do you differentiate the two? Explain this in class. Good. You can look at your notes. There you go. So with movement of mass with a force. So what does that mean? That you don't care about concentration. It's like the potassium calcium pump. We don't care that there's more potassium outside, we're gonna put more potassium outside because we have a pump. Same here, it doesn't matter what's the gradient is, you can just push. So that's the difference between diffusion and convection. In convection, you have a force, requires energy. And a longer scales is quicker because you're using energy. You can maybe have more mass, sure. But it's with a force. With diffusion, it's the same, but what changes? We need assist. So, it's like that. Convection, whatever. Right, so we have diffusion, or what's that all about? We would movement or something, right? Movement of mass. What is it moving? There you go. Hello. How are you doing? You good? What's your name? Jada? Nice to meet you, Juan. Or, I would say. I like people to call me Juancho. To put it here. There you go. So yeah, that's the difference. What's your question? Or what's yours?
Yeah, I think I was asking.
Oh, yeah, okay, so we describe the difference. So in what part of your body you feel, or anybody, feel that there's a force applied to move mass? Where? I know an organ that does that. Multiple action. They're applying a force. Is it hard? What else? The what? Sure. Maybe your lungs too. You're like contracting to get air in and out. So that's that will be an example of convection. You have your heart pumping or your lungs contracting and dilating in order to get air in and out of your system. That also, yeah. Like that's basically anything that you do mostly that requires energy. It has to do with transfer of something. It will be a type of convection. Yeah. Does it make sense?
Yeah.
Jada, you have any questions? Oh, okay, we have questions. What is it about? Do you have it? You have it with you? Let's work on it. Let's. There's so the P equal to velocity, the length scale of so L. I think it was, it said alpha. Yeah, but do they use alpha or you don't? Ah, like this. Cool. So we have the velocity, length scale, and the diffusion coefficient, right? And what does P mean? Okay. So here we have the diffusion coefficient. That's cool. And then we have the velocity too. And then so we are trying to look for the length scale, right? Oh. Wait, what? So the oxygen diffusion coefficient is this. It's the velocity. So is it P a constant? So P what? The Clad number. And the finance of the transfer. What do you find that equation here? Oh, the textbook? Of course, man. No, it's not a constant. No. Oh. In that equation. Which one here? Here? This one? It has to do with what it means. So if E is equal to 0, then like convection is negligible and diffusion dominates. It's equal to 1, diffusion and convection occur. in an equal manner. And then if it's towards infinity, then diffusion is negligible, and then convection it's like, okay, that's a good explanation. So what's the question asking? Let's see.
This kind of like, I think you mentioned that value before. Of how
Yes.
that value.
Yes, it has to do with that. So something that we were like, we're talking about that Dr. Lewis is gonna explain later, is that for if we have an equation, a graph of length scale to be in the x-axis, in the y-axis to be transport time, then diffusion so basically this what it says is that for small scales diffusion, it's going to take less time to transport a material. But for longer scales, convection, it's going to take way less time for the same material than a longer scale. So for example, if you need to move something, let's say 50 micrometers from point A to point B, you will use diffusion. It will be more efficient, it will be faster. So by a concentration gradient, you will get this job done quicker. So then if you have point A and point B being like meter, yeah, at that point convection is the way to go. You apply a force to the flow, so you can go to point A to point B. So in this problem, what you're doing then is using this knowledge that you're gonna get on Wednesday and see what PE gives you. So we said that if 0, we said that it has to do with diffusion being dominant. 1 equal, and then infinite, meaning that convection is dominant. So it's asking you to so how large the distance has to be so that convection is dominant. And then it asks you, why do you think that diffusion is important in physiological systems? Listen to this is like based on that, you're gonna see like, oh yeah, small scales, this thing is close to 0, therefore diffusion is dominant. Larger scales, and then you get to write it down when this thing is really close to infinity, convection is more it's dominant, therefore for a physiological system that's really small, like capillaries, like cells, stuff like that, diffusion will be the way to go. If you're talking about like blood going in your stream, like force has to be applied so blood can go to your stream. So it depends. Does it make sense? Mm-hmm. All right. Fortunately, officially, the learning hours are complete. All right. That was exciting, guys. Thank you for coming. Had fun. You had fun? Can be honest. I want. I tried. Let's see, how do I do it? Stop.